Hello, everyone. In the world of electronics, there are these tiny, unsung heroes, components that are basically bodyguards for our most sensitive circuits. Today, we're going to get to know one of the most important of these guardians, the Zener diode. So let's jump right in and see exactly how this thing works.
So let's start with a question that sounds, well, a little dramatic, but it's actually super practical. Why doesn't your phone or your laptop or that expensive gaming console just fry itself the moment you plug it into the wall? It's a fair question, right? Especially when you think about what's really going on with the power coming out of that socket.
And here's the heart of the problem. All our precious electronics, they're designed to run on a very specific diode. Stable, clean, direct current, or DC power. But the power that's coming from our wall sockets, it's this wild, fluctuating thing called alternating current, or AC. And that mismatch, well, that's a huge problem that has to be solved before that power can safely get anywhere near the delicate brain of your device.
So this brings us to our first major challenge. How do we tame that wild AC power to protect our circuits from all those unpredictable surges and dips? To really get the solution, we first need to take a quick step back and remember how a normal diode is supposed to behave.
A standard diode is kind of like a one-way street for electricity. You put voltage on it one way, the forward direction, and current flows easily. But if you try to force current to go backwards, what we call reverse bias, its job is to completely block it. But if you apply too much reverse voltage, you hit this point called the breakdown region. And at that point, poof, the diode fails, current just floods through, and for most diodes, this is the absolute danger zone. Game over.
But what if a component didn't fear that breakdown region? What if a component was specifically designed to live there and use that so-called danger zone to its advantage? Well, that's where our hero comes in. It's time to meet the Zener diode.
The crucial difference is right here in the definition. Unlike a regular diode, a Zener is heavily doped. Now that just means it's built with specific impurities that totally changes its electrical properties. And this special construction allows it to not just survive in the breakdown region, but to operate there reliably, day in and day out. It's literally engineered to thrive in the exact conditions that would destroy a normal diode.
And this graph shows it all so perfectly. Look, in forward bias, it acts just like any other diode. No surprises there. But in reverse bias, once it hits that special breakdown voltage, look at that line. It's sharp, almost perfectly vertical. The voltage stays almost completely constant, even as the current going through it changes like crazy. This isn't a failure. This is the Zener's superpower. It's not a bug, it's a feature.
Probably the best way to get your head around this is with a simple analogy. Just picture a big dam holding back a reservoir of water, okay? The water level in that reservoir represents voltage, and the dam's main job is to keep a constant water level for the town downstream no matter how much it rains into that reservoir.
So how does this Zener diode actually pull off this constant voltage trick? How does our dam really work? Let's dig into the physics behind its very unique ability.
The phenomenon itself is called Zener breakdown. It's that precise point where the diode basically says, okay, the voltage is high enough, and it opens up its own special spillway for current to flow, but in a very, very controlled way. The real magic here is that while it lets all this extra current pass through, it locks the voltage across itself at a nearly constant value.
Let's go back to our graph because this is so important to see. That specific voltage where the breakdown happens is called the Zener voltage, or VZ for short. In our dam analogy, VZ is the exact height of that spillway. The second the water level, the input voltage, tries to go above VZ, that spillway opens up and drains all the excess, keeping the level right at VZ.
Okay, now that we get the theory, let's see where this becomes incredibly useful in the real world. We're going to look at the Zener's most common and honestly most important job, being a voltage regulator.
This little circuit diagram shows the Zener diode right in its element. I want you to notice two really key things here. First, there's a resistor in series with it, and that's there to limit the total current. And second, the Zener itself is placed in parallel with our load, and the load is just a sensitive component we want to protect. And of course, it's hooked up in reverse bias.
So let's walk through this step by step. First, you've got an unstable input voltage coming into the circuit. That's our fluctuating reservoir. Second, the Zener diode is just sitting there monitoring that voltage. Third, now here's the magic. If that input voltage tries to go above the Zener's rated voltage, VZ, the Zener instantly starts to conduct. That's our spillway opening up. Fourth, it diverts any of that excess current safely away to ground.
And finally, because that Zener is in parallel with their load, the voltage across the load gets clamped. It literally cannot go higher than VZ. So the load gets a perfectly stable voltage. Pretty cool, huh?
All right, let's focus in for a minute. If you're studying for an exam, this next part is what you absolutely positively need to know. These are the main takeaways.
Okay, let's quickly recap the key facts. Number 1, and this is the big one, it operates in the reverse breakdown region. Number 2, its whole purpose in life is to maintain a constant voltage, which we call VZ. Number 3, in a circuit, it always needs a series resistor to limit the current and protect it. Number 4, because of all this, its primary job is voltage regulation. And finally, number 5, its special power comes from being a heavily doped PN junction. Make sure you have these 5 points down cold.
And last but not least, you absolutely must be able to recognize this symbol on a schematic. It looks a lot like a standard diode symbol, but you'll see the cathode line is bent into this little Z shape. Z for Zener. It's a really easy way to remember it, and trust me, you will be expected to know this one.
So we've seen how the Zener diode acts like a voltage guardian, just standing watch to maintain perfect stability. And this brings me to a final question for you to think about. What other types of guardian components exist out there? What protects our circuits from other threats, like too much current or maybe electrical noise? That's a great topic for another day. Thanks for listening.